Hi guys. Okay, so we are going to do day 6 and unit 6 today, and we're going to focus on the second fundamental theorem of calculus and what an average value is. So those are going to be our two big things today. So let's kind of start with this exploration. So I want us to go ahead and find this antiderivative. So I'm going to rewrite it as the power rule and go ahead and take the power rule. Now remember, when you add 1, that's not -4, that's -2. And we don't need a plus c because we're evaluating from a to b here. So I just am going to go ahead and rewrite and do finally my antiderivative evaluated at b minus my antiderivative evaluated at a. Remember, squaring a negative is still a positive, and then the minus was there. Okay, so that would be if I wanted to take the antiderivative. But now let's find, so that's still like big F of x now. Okay, but now let's find the derivative of what we just found. So if big F of x was what we just had, what's the derivative of that? So I'm going to rewrite again to the power rule and then take that derivative. And what do you notice? Hopefully you notice that this right here is the same as this inside right here with the exception of a variable change. Okay, and that's kind of what we're going to be doing with this second fundamental theorem of calculus, is seeing that basically if I wanted to take from where I started and find if this was big F of x, and I wanted to take the derivative without all of this work in between, it's going to be this guy filled in at the x. Now, it's going to change a little bit if we have something like a 2x here. If there was a 2x in there, then I'd also have to do a chain rule and multiply by the derivative of that, which would be 2. Okay? And that's basically our second fundamental theorem of calculus here. So if I go from some number to a variable, or a function of x, we can say it, okay? So we just get out what that inside is. However, if it's not just the x, if it's like the 2x or an x squared, we have to apply the chain rule and also multiply by the derivative of what that was, okay? What that bound was. Now, we can take this a step farther, and let's say that both of the bounds were functions of x. So here this was a number, but if I had both bounds that are functions of x, then I can go plug in the top bound times the derivative of the top bound minus plug in the bottom bound times the derivative of the bottom bound. Okay, and that's what we're going to see. Now, how is that different? Let's say that I just wanted to take the derivative if I had two numbers of some function. Well, if I had two numbers of some function, then this right here is going to end up being a number that I'm going to take the derivative of. And the derivative of that number would always be 0. So we are only looking at this when we have a bound that is a function of x of some sort. So let's try it for this one. We don't need to go through all the intermediate work. I can see that I'm going to go ahead and plug in my bound into that t, but now I have to do the chain rule and multiply by the derivative of that bound. And we can clean it up as much as we want, or to match a multiple choice. Okay? Okay, let's look at the next one. Now I have a bound on both ends. So I'm going to go ahead and plug in this one, oops, squared to the third, with my chain rule, minus, plug in this bound, and I don't have a chain rule, that's just a 1 for the derivative of x, and then we can clean it up. Okay? Now, that's the derivative. The question, though, now asks to find that derivative evaluated at 2. And if you want to simplify, you can. Oops, 1/8. Oh, that looks horrible. 1/8. Make sense? Okay, so we're going to look at one more example together, and then I'm going to let you try some. So what if the function was at the bottom bound? Then we've basically kind of been plugging in this top bound and taking the derivative, and that goes away. So this is going to end up being the negative part, that second part that we are subtracting. So this bottom bound, I'm going to have a negative out in front when I go to plug it in, and then times the chain rule. So if it's only in the bottom, then there's a minus out in front. So just like that second piece, where was I? On this one, this was just the bottom part, but I had a minus out in front. Same thing. We just don't have the first part. And then we can clean that up as much as we want to. So -4 over x to the 5th. And this one actually wants me now, so that's what the derivative is. This one now wants me to find the derivative evaluated at 1. So I would get out -4. So I would like you to try the next AP question on your own and see how you do. The answer is E. Make sure that that is okay. So you're never, ever, ever taking the derivative of the inside part. So that inside part is what you are plugging something into, but you never take the derivative of the inside of that integral. Okay, this next AP question is a little bit different. So here it wants me to know where g is decreasing. Well, g is decreasing when the derivative of g is less than 0. So I need to go find the derivative of that g. So the derivative of that g, see I have this bound with an x, so I'm going to go plug it in. And there's no chain rule here, and then the bottom bound is a number, so that derivative would go to 0, that's gone. And so now I'm going to go ahead and look on my graphing calculator and look where this is less than 0 on the interval from -1 to 3 only. So see where this function is graphed less than 0. Not less than or equal to, just less than. And after you get your graph, go see what you get. Hopefully you got one of the above, and we can check in class if you didn't. Okay, this next part is just to check your understanding. I want you guys to pause me. I would like you to try 7, 8, 9, and 10, all of the A, B, C, D, and then when you're ready, unpause and check. Zero. And last one. Oh, oops. There. That one goes here. All right. So if you had questions about that, please, please, please let me know in class. And okay, so this one wants to know for what values of B does this one have a minimum? So I'm going to go ahead and say kind of like let that equal some type of function y, whatever. So I'm going to go ahead and find the derivative. So that would be the cosine of e to the b, and then the derivative of b would be 1. So I'm going to find the 0 here, and I'm only looking between 0 and 2. And when I go graph, I get to graph something like that. So this guy would have to be the min, the relative min, I mean. And then we just need to go check our endpoints as well. Well, we know that 2 won't be included because it's going to start increasing from there. So really the only ones I have to go check now are 0 and whatever this value is. So go find this value on your calculator. I got it to be 1.550. Plug them in right here. So go to Math 9 and go see which one gives you the smallest number. I got the smallest number to occur here when I went and plugged them in. Make sure you get the same thing. This one gives me a 0, and this one gives me a value less than 0. So now I need to answer the question. This question said, for what value of b? So the value of b is that x part that I was plugging in here. I guess this could have been b instead of x, but yes. So I'm going to find that my answer is D. All right, so I would like you guys to try this one on your own and see if you get A. Hey! Okay, so the next concept that we're going to be talking about is called the average value, or the mean value theorem, or mean value for the integrals now. So if I have like some function of x, maybe it's a position, maybe it's a velocity, okay, maybe it's an amount, but I have this, so if this is position, then when I find the average value, I'm kind of finding the average position. If this was velocity, then I would be finding the average velocity. So you're finding the average value of whatever that function inside is. And the way we're going to do that, we're kind of like evening out. So if we have this curve, we're finding that whole area under the curve. And then we're going to average out to kind of make it into a box. So it's just evened out from the top and what's above and what's below to get the exact same area in this box as I did under the curve. This output value is the average value. Oops, just lost. Well, let's try another color maybe. Not quite sure. But that output, I would write, is the average value. Okay? And I'll let you kind of read through and think about that. And then I'm going to take you through a couple real life scenarios. So here, a lot of times the billing companies will let you kind of pay this constant bill for your electric or for your water, but they're letting you pay a constant because they're saying some months it's higher, some months it's lower, but this is what we're predicting to kind of be the average bill. So this is like the average value. I still don't know why that's, let me turn the drawing off maybe and then turn it on. Okay, there. So this output of the amount you're going to pay is kind of the average value. It's the average money in this case, that's your average bill that you would pay. So they like to see, oh, okay, it's easier for you at home, like paying your bills, to not have this big flux in your expenses every year or every month. And so you can pay this more constant. Now they may have to adapt it a little bit, but because the billing company, they don't know exactly how much you're going to spend. But another way I kind of like to think about it is the polar ice caps. So let's say that this polar ice cap was my function of x, okay? So my function of x is maybe the height of where the water is going to be. And so I've got some of the like some is below, some is above. And I know this is kind of sad to think about, but we're always talking about how the polar ice caps are melting and what's that going to do to us. So when they're melting, they're going to increase like the water level because we've already got some above, and so it's got this function and this flux. And so we're kind of going to look and say, well, once all of these melt, what is the new water level kind of going to rise to? So what is that average value of the height here? What's that average height of the water going to be? And so that's going to kind of like let me know, oh, okay, like water levels rising, it may go out to the land, and I need to know this stuff. So we can, as mathematicians, create this function over and find where that average is going to be. Now, of course, there's more variables, with water evaporation or expansion, with the temperatures, or, all of that. But those variables will take into account when you become higher level than me. Okay? So let's look at this one. This function is some type of function. I don't know what it represents. It doesn't say, okay? Maybe it's the height of the water level, okay? But I want to find the average value of this function from 0 to 3. So in order to do that, I have to integrate that function from 0 to 3 and then average it out, okay? So the average value basically is like this 1 over b minus a times the integral of f of x dx from a to b. And so you can either think of it as all divided by the b minus a, or you could pull it out in front. So that would be kind of like that 1/3 out in front, the integral from 0 to 3 of 4 minus x squared dx. So I can take that 1/3, I'm going to go ahead, just leave out, take the antiderivative, and evaluate from 0 to 3. So first I'm going to plug in my 3 minus plug in my 0, and then simplify, to what you want. And I got an average value of 1. So let's kind of like look at this graph right here. So the graph is a parabola facing down, shifted up 4. I know my zeros are -2 and 2. Okay, but I'm looking from 0 to 3. So I've got some of that. Let's get rid of that arrow for a second. This is going to go below. So I'm going to 3. Okay, so as I'm doing that, what would 3 actually be? Let's see. 9, so -5. 1, 2, 3, 4, 5. At that 3. So I want to find the average value from 0 to 3. So I've got some of the height that's below, some of the height is above. And if I found that area, then my area is just the inside. That's the area. When I take it by the third, it is now finding that 1, if I went and did this right here, it's going to give me the exact same area as what I just found. Okay, it's giving me the same area as what I found in that orange. So these are exactly the same areas, this purple and the orange, just we've created it into a rectangle. Super cool. But where does that happen? that output of 1 is that average value. Okay, so again, it's maybe saying some is below, some is above, and we want to average it out. So if I wanted to talk about average velocity now, I want you to see how you can do this in two ways. We always know that the average velocity is the change in position over change in time. So we always did the position over time. But I want you to see now, if I want average velocity, I could integrate the velocity function and average it out. Because this is the change in position over the change in time. It is the exact same thing as what we've already learned, maybe back from pre-calculus days of this right here, of an average velocity, okay, but definitely from earlier chapters here. So if I want an average velocity, I could integrate the velocity and divide by the b minus a. So whatever that function is on the inside, what we're doing, this process, gives me that average output value of that function on the inside. Okay? So how could I do average acceleration? Well, I could integrate the acceleration function, and I'm going to go ahead and just write it here because that's the same thing as divided by b minus a, which is the change in velocity over the change in time, which we already knew. Ah, love it when things connect, don't you? Okay, if you want to go ahead and try to fill this in, go for it. Okay, this is a great thing to try and to check with me on my notes that I have. All right, so let's try this AP example. The velocity of the particle is v of t, and the acceleration is a of t. Which of the following gives the average velocity of the particle? So I know that I could be looking for two things. I could be looking for the integral of the velocity divided by the change in time, or the change in position over change in time. So all they have given are either acceleration or velocity functions. So here I can see that my answer is B. This gives me the change in the position, okay, the integral of the velocity, and then the 1 over b8 minus 0 is that change in time. All right, so go ahead and try this next one on your own. You can pause me and see if you get A. And in fact, I want you to go ahead and try this whole last page on your own. It's got some review built in as well. And when you're ready to try, you should get E, C, B, and 23.055 or 54, depending on if you truncate it or round. All right, see you in class.